subscribe now and press the bell icon. Never miss an update.
Hi students. Now in the last class I have given you some concepts of elementary concepts of light and so on. Now remember, see, light is a form of energy. And anything that we see around us is called source, maybe luminous, non-luminous, and from a source, whether it is this or that. Now light energy is given out in the form of continuous in all directions, in the form of rays. Now ray is path of light energy. So that this represents the path, this represents the direction. Now, see, we are seeing that the reflection, see where light, ray, beam of light or ray of light falls on a mirror like this. This is sent back. This is reflection. Now this is incident ray. This is reflected ray. This is reflecting surface. Normal thrown at the point of incidence. This is angle of incidence, angle of reflection. Now, the laws can be stated like this. The incident ray, the reflected ray, and the normal. Incident ray, the reflected ray, and the normal are in the same plane. And the angle of reflection is always equal to the angle of incidence. So these are the two laws. Now I also gave you the concept of image. See here, if you have a mirror, let's suppose a plane mirror, if you give an object, source, it sends out light in all directions in the form of rays. A ray going like this obeys these laws. So here I draw the normal, measure the angle of incidence, measure the angle of, construct equal angle on the other side. Now this is reflected. I take another ray, say for example, normal incident. Now normal incident means the angle of incidence is 0. Therefore you have the reflected ray like this also. The two rays meet here. Now this is known as the image. Therefore image is the point where the rays after reflection meet either actually meet or meet when produced backwards. Now, when they meet, if they are produced backwards, that is called virtual image. Like that. Now, I also give you the concept of spherical mirrors. Spherical mirrors. If this surface, reflecting surface, is not plane, if it is curved, then we call it spherical mirrors. So you have a mirror like this. This is a part of a sphere like this, let us suppose. At the center of the sphere, of which the given mirror, spherical mirror, forms a part. See center curvature. The geometrical center is called the pole. Now this is the axis. This is the axis. Now there are two types of mirrors. Mirror with center curvature in front and the mirror with center curvature behind, like this. This is part of this sphere, let's suppose. Then this is the back of the mirror. This is pole of the mirror. This is the axis like this. Now this is called concave mirror. This is called convex mirror. Now, I'll take a ray incident on the mirror, traveling parallel to the axis. Incident on the mirror, traveling parallel to the axis. I apply these laws and see where it goes. Now here, this is the normal, because see, lying on the center to any point on the sphere is radius, it is perpendicular to the surface at that point, therefore this is I, and this is R. Now this point is called the focus. This point is called the focus. Now similarly here, if I draw the normal, I, R, so this when produced backwards is called the focus. Now, what is to be observed is, see, it is not only this ray, all rays that are parallel to the axis, like this, like this, like this, parallel to the axis. They go through this point. Now that point is principal focus. The same thing is true here. The same thing is true here. This is the normal. So it goes back like this. Now observe, we have 3 points in both the mirrors. One is the geometrical center of the mirror called pole. Center curvature, the center of the sphere of which the given mirror forms a part. Center curvature, the center of the sphere of which the given mirror forms a part. Now all rays parallel to the axis fall into the concave mirror. After reflection, observe, they meet at a point which is situated on the axis. Now here, all rays traveling parallel to the axis after reflection, see, when produced, meet at a point, focus. Now here, so there are 3 points here, P, 4, principal focus, center curvature. And there are 2 distances. Distance between the pole and the focus, distance between the pole and the center curvature. This is what we call focal length. This we call radius curvature. Here also, the radius curvature, the focal length. we had mentioned a sign convention, that is, distances measured along the direction of light propagation, that is, this distance is taken positive in the direction of light propagation. Distances measured, see, this is positive. Now distances measured in the opposite direction, see, we measure from here to here, so that is taken negative. Measure in the opposite direction, that is taken negative. Now this is all what we have discussed. Now today, we will find the relation between these two distances. Now that forms an important,
Yes.
Now derive the relationship between the radius of curvature and the focal length. The radius of curvature and the focal length. Here, I will derive for one mirror, it can be followed for the other also. Now I consider, let's suppose, a concave mirror. The moment I write the mirror, I must mark the point, the fixed point. This is the back of the mirror. Now this is part of a sphere whose center is here. Therefore, this is center curvature. Once I am toward the mirror, these 2 points can be located. This is the axis, principal axis. I take a ray. Traveling parallel to the axis, of course, close to the axis. Though I have drawn the figure, the ray far away from the axis. In practice, this incident ray, let us say, OA, is traveling very close. Now this is the normal. The case of a sphere, easy to draw the normal. Just join the point of incidence to the center curvature. That gives you your I, the angle of incidence. Consider equal angle on the other side, that is angle of reflection. Reflected. The reflected ray meets the axis at a point that we call the focus. Now, here you have to remember that if 2 rays are parallel to the 2 straight lines parallel to each other, this is transversal, therefore this is alternate angle. Consider a concave mirror of 4 feet and a center curvature C. A ray OA traveling parallel to the axis and close to the axis. Passes through here. Now, from the figure, OA is parallel to axis PC. AC is transversal. Therefore, angle OAC is equal to angle ACP, alternate angles. Since OAC is I, ACP is also equal to I. Point 1. Now, in the triangle, AFC, in the triangle AFC, angle ACF is equal to angle CAF. The ACF is I, CAF is R, therefore they are equal. Therefore, it follows that, say, angle AF is equal to, side AF is equal to CF. AF is CF, isosceles triangle. Isosceles triangle. Now, see, make an assumption here. See, if I take a mirror P, C, C, yeah, it's not this ray I am considering. See, if I consider this ray, this is the normal, this is the I, R. If I take a ray very close to this, say for example like this, this is the normal, this is the reflected ray. See, here it is found that AF is almost equal to PF if this ray travels parallel to the axis, close to the axis. So I make that assumption, if and only if A is close to P, very close to P, it also means that if the aperture of the mirror is very small, then CAF is almost equal to PF. If I write this AF almost equal to PF if this is very close to like that. Now, again in the figure, from the figure, see PC is made up of PF plus FC. PF plus FC. Now FC is AF, but AF is equal to PF. So this is equal to C PF plus FC is AF and AF is PF. Because AF is CF and that is nearly equal to PF. So we can write this equation. But PC is R, PF is F, PF is F. That is, since PC is R and PF is F, we have R. Remember, this is R is measured in this mirror like this, therefore it is minus R. F is measured like this, it is minus F therefore. So it is minus R is equal to minus F. I am substituting here minus R. Minus R is minus 2F. In other words, R is 2F. R is 2F. Or F is R. So that is the relation between R and F. Now that can be true for the other mirror also. We'll go to another important relation, mirror formula. Or the relation between object distance image distance and radius of curvature. Or deriving the relation 1 over F is equal to 1 over V plus 1 over U. So this is an important derivation. Now, again take the case of concave mirror. For center curvature, principal axis. I'll keep an object extended object having some size placed at right angles to the axis. Now I have taken a concave mirror of chord P and of center curvature C. So therefore this is the axis. I have placed an extended object OP at right angles to the axis of the mirror. Now from the topmost point P, I take a ray incident at P, making an angle I. It reflects along PM such that I equals R. Another ray passing through C falls on the mirror normally because this is a sphere and this is the center. Line joining center to any point of the mirror sphere falls normally, therefore it retraces the path because I is all 0 here, R is 0. So this is the point of intersection of the two reflected rays. So this is one reflected ray, this is another reflected ray. Now the point where the reflected rays meet is called the image. Now Therefore, M is the image of B. Image of B. Now, what happens from B happens from all points. Because I have placed this at right angles, I simply draw Mi perpendicular. Therefore, Im is the image. See, of OB. Formed as shown in the figure. That means I have to take two rays from B, make them fall on the mirror, see where they meet. That's the point of image. I draw the perpendicular from that point to the axis. That gives the image. Now observe, there are several triangles here. Triangle formed by the object at the pole and triangle formed by the image also at the pole. See, triangle POB. Object forms a triangle with P there over there. See, and triangle PIM. Notice this is perpendicular, therefore the angles of 90. Now this is I, this is R. So three angles of one are equal to three angles of the other triangle. Now such two triangles are called similar triangles. Similar triangles. So they are similar. Now if the triangles are similar, sides are proportional. You have to write the sides opposite to equal angles. See, I, opposite to I is OB, equal angle R, opposite side is IM, that must be equal to, see this angle, the third angle must be necessarily equal. Opposite to the third angle OBP, the side is PO. Opposite to the equal angle, see IMP, the side is PI. I will call this equation 1. Again, consider the other two triangles. Triangles formed again by the object and the image, but another fixed point. This is a fixed point, this is a fixed point. Object forms a triangle at this point, image at this point. So therefore, the angles, right angle, this angle here, vertically opposite angle, equal. So two angles are equal means the third angle is necessarily equal. Therefore, again, you have triangle formed by the object at the center curvature, COP. Object, center curvature. Triangle formed by the image at the center curvature. See here, they are similar. Now therefore, OB, the object, IM, image, is CO by CI. I will call this equation 2. Now observe these two triangle equations. There is common sense here. So from equations 1 and 2, from equations 1 and 2, we have PO by PI is equal to CO Now again, from the figure, look at the figure there. CO is made up of, or can be written as CO, PO minus PC. So it is PO minus PC. CI, PI minus PC. So we call this equation 2. Now observe here. See, all distances are measured from pole along the axis. This is the object distance denoted by plus. Because we measured against the direction of light, this is minus against the direction of light. Now this is image. So from pole to the image is minus V. From pole to center curvature, so it is minus R. Minus R. So you have PO there. PO. It is minus U divided by minus V. That is equal to PO, again minus U, minus of minus R, divided by PI, minus V, minus of minus R. Cross multiply, till this becomes plus. So you have U minus V. From equations 1 and 2. See, the left hand sides are same, therefore comparing the right hand sides, we have PO by PI is CO by CI. But from the figure, CO can be written as, CO can be written as PO minus PC. PI, CI can be written as PC minus PI. Now from the figure, we denote the distance PO, distance to the object O from the pole as U. According to sign convention, it is minus U. Distance to the image from the pole measured along the axis opposite to the direction of light, minus V. That is equal to PO, again minus U. PC, distance to the center curvature from the pole, it is R, opposite to the direction of light, therefore minus R. Similarly, minus R, minus of minus V. Cross multiply and simplify. We have UR plus minus UV, that's equal to UV minus VR. Rearrange the terms, we have 2UV equals UR plus VR. Dividing all the terms by UVR, we have the separation. Since R is 2F, you can also write this as 1 over F as 1 over P plus 1 over U, as R is 2F. Substitute it here, you get 1 over F. So that is the relationship between the object distance and the image distance. Notice that you can keep the object at any distance. This is variable. Similarly, this is variable. But on the right hand side, the left hand side, you have the constant. You have the constant. Now here we have the concept of the magnification. See, for instance, see if I had kept, say, the object here, the image size would be different. We will come to it shortly. Now there is size of the image here, size of the object. Now one is compared to the other. Now that is in the concept magnification. magnification is defined as the ratio the size of the image to the size of the object. That is denoted by the symbol M. Usually, M is image size or object size. This also means, see in our with reference to our figure, it is image size or object size. That is will obtain expression for the magnification. This is the definition of magnification. Now let us suppose from the same figure, say triangle POB is similar to triangle PIR that we have come across in the derivation. Now therefore, object size over image size is equal to object distance over image distance. We can take the reciprocal image size or object size, that is PO over PI. Now apply the sign convention here. See, IM is measured below the axis, therefore it is minus IM over AB. It is OB plus OB above the axis. And PO, again the direction reciprocal on both sides, minus V over minus V. But IM over AB is by definition magnification. Therefore, minus M is V over U. That is, M means for a concave mirror, it is V over U. This is the definition, this is the expression for the magnification. For the day, that's all for the day. We'll continue next class.
Subscribe now and press the bell icon. Never miss an update.